Students, welcome back to our next session. Here we are going to see the next topic on inductive type sensors, where we are going to discuss about LVDT and RVDT. It is very important topic in this unit. So here you can see the motion sensors and potentiometers we have completed. Inductive sensors LVDT and RVDT we will take up today and we will complete in this session. So inductive type sensor, there are actually three types of building blocks in electrical system, or we can say three transducting principles by varying the resistance, by varying the capacitance, by varying the inductance. So this is of a third type, inductive type sensor. So we are going to vary the inductance in the in the sensors. So the change in inductance is directly proportional to the measurand that we are about to measure. The property of an electric conductor or circuit that causes an electromotive force to be generated by a change in current flowing. So here inductance is equal to nu naught nu n square G. L is the inductance of the coil, nu naught is the permeability of the air, and nu is the relative permeability, n number of turns, G coil geometry. So this is the governing equation or principal equation in change in inductance to measure. So here linear variable differential transformer, so in short it is known as LVDT. You should never call it as transducer. It is linear variable differential transformer. So by mistake many students used to call this as transducer. Please avoid that. A transformer with a primary coil and two secondary coils. So this is having one primary coil and two secondary coils. So this is the construction of the LVDT. You have AC input and you have secondary coils and you have primary coil. So this is primary coil and you have secondary coil. These are the two secondary coils. This is one secondary coil and this is another secondary coil, and in middle this is the primary coil. So input is given to primary coil and output is taken from the secondary coils. So that is the construction, very simple construction. And you have a core. So this is the core, and when it moves, when it is at the middle position, this is known as null position of the LVDT. When it moves either direction, then it deflects the null position. And this is the plunger attached to this core, and this plunger is having the end, and to that end we are going to attach the object for which the displacement to be measured. And this is simple in construction. Three coils symmetrically spaced along a insulated tube. I will show you the construction also. The central coil is the primary coil and the other two are identical secondary coils. Secondary coils are connected in series in such a way that their outputs oppose each other. A magnetic core is moved through the central tube as a result of the displacement being monitored. So here this is simple construction of LVDT. When there is an alternating voltage input to the primary coil, alternating EMFs are induced in the secondary coils. So that is the according to transformer principle. Since they are so connected that their outputs oppose each other, the net result is zero output. When the core is displaced from the central position, there is a greater amount of magnetic core in one coil than the other. The result is that greater EMF is induced in one coil than the other, and then there is a net output from the two coils. The bigger the displacement, the more of the core there is one coil than the other. Thus the difference between the two EMFs induced increases the greater the displacement of the core. So typically LVDT is having operating ranges from about plus or minus 2 mm to plus or minus 400 mm. Non-linearity errors are typically about plus or minus 0.25%. LVDT is so here this is very smaller, so it is almost a linear type of instrument, and LVDTs are very widely used in monitoring displacements. So this is the LVDT overall principle, and if the core is displaced from null position in either direction, one secondary voltage will increase while the other decreases, since the two voltages no longer cancel, and a net output voltage will now result. So this is the simple working principle of LVDT, and I will show you the construction in next slide. So here this is the core. It is obviously a magnetic core, and in middle we have primary coil, and this is support, spring support, and here this is the probe and the probe tip to which the object is attached, and the actual output characteristic curves are seen here, and this is ideal curve, and this is actual curve. So this is negative side of displacement and positive side of displacement, and this is a simple circuit diagram, and AC is given to primary coil and this secondary coil. So input voltage is given here, and output is taken and measured through a voltmeter. So this is simple construction of LVDT, and I will show you the cross sectional color diagram. So here you can see this is the cross section, and you can see the core here. This is the core, and you have primary coil, and these two are secondary coils, and it should be shielded properly. That is very important. Magnetic shielding, and end caps are provided for any. There should not be any opening, and it should be shielded properly. Otherwise it will interact with environment factors. And this is signal conditioning circuitry. There is a inbuilt signal conditioning circuitry, and signal conditioning we are going to see more about it in another unit. It is second unit. Still we have to cover it, and we are going to see in depth of signal conditioning there. And this is epoxy encapsulation for shielding purpose, and this is a high density glass filled coil forms. So this is for all this shielding is provided to arrest the leakage, or what you call the interaction of the coil with environmental factors. So three types of LVDTs: unguided armature, captive armature, spring extended armature. So first one is unguided armature. So here a measured object is connected to the probe, and armature must be attached to the specimen, and armature fits loosely in the bore. So here there is no guided, it is loosely fixed here. This armature is nothing but core. The body must be separately supported and properly aligned. So here the body that is the coils should be properly placed, and elevation cross section view. This is the cross sectional view, and when you see it is not a guided one, and there is no supports provided for this core movement, and it should be properly placed and aligned always. So that you have to ensure always in this type. Unguided armature, there is no wear on the LVDT because no contact is made between armature and bore, and LVDT does not restrict the resolution of the measured data, infinite resolution. And here unguided armature. So here this is the cross section view, and it is an unguided type, and whereas in previous one, right? So here this is unguided support. So the core is moved unguided way, and it should be properly placed and aligned always. So unguided armature well suited for short range, high speed applications, vibrations, So here this is the displacement with respect to time, right, and this is the motion, right, for this movement, right. The displacement is measured and the waveform is drawn. Captive type. So in captive type, you have guides, and you can see these are the rollers or balls. So these will maintain the alignment of the core movement. That is very important here. And this is the object for which the displacement is being measured here. And measured object, armature must be attached to the specimen, and same construction except this guides. Armature is both guided and restrained by a low friction assembly. Body must be separately supported. So this is an improved construction from unguided type. So next is spring extended armature. So here the core is actually supported here by a spring, and the internal spring to continuously push the armature to its fullest possible extension. So here it will force the core to be at its initial position always. So that is another improved construction from the captive type. Spring extended armature. So here in this type, the spring extended armature is best suited for slow moving applications. Attachment between armature and specimen is not required. So these are the characteristic curves for AC and DC, and you can see this is the full range, and the core position when it moves this side, this is negative displacement, and this side it is positive displacement, and magnitude of differential AC output. So this is y-axis, magnitude of AC output, and you can see in next graph it is the phase angle output relative to the primary coil. So this is the phase angle of the primary coil, and in next curve it is the output from the electronics. It is DC output. It is DC output. It is it almost follows the ideal curve. This is ideal curve, and these are the three characteristics. You can see this is null position, and this is maximum left position, and this is maximum right position. When under these three positions, the curves are taking place in this way. So these are the characteristic curves for AC and DC. So AC LVDTs, advantages compared to DC LVDTs are smaller in size, more accurate, can operate within a wide temperature range, lower unit cost. So DC LVDTs, when you compare with AC LVDTs, these are the advantages: ease of installation and signal conditioning. Always when you are dealing with the DC type of devices, the signal conditioning is always simpler. Signal conditioning equipment is part of the LVDT itself. Can operate from dry cell batteries. Usually low system cost. It is always cheaper DC devices. Uses automation machinery, civil structural engineering, power generation, manufacturing, metal stamping, forming, OEM, pulp and paper, the industrial valves, R&D tests, automotive racing. There are so many applications. And in civil structural engineering, we can see displacement measurement of embedded concrete anchors tested for tensile, compression, bending strength, and crack growth in concrete. Deformation and creep of concrete wall used for retaining wall in large gas pipe installation. Dynamic measurement of fatigue in large structural components used in suspension bridges. And to summarize, LVDTs are robust equipment for measuring deflection. AC LVDTs require separate signal conditioning equipment, while DC LVDTs include signal conditioning equipment on the device. There are three types of LVDTs: unguided armature, captive armature, and spring extended armature. AC LVDTs cost less than DC, but the entire measurement system must be considered. Next version of LVDT is RVDT. Whereas in LVDT you found the linear motion, whereas in RVDT rotary motion. That is only difference. Otherwise, the construction, everything is same as LVDT. A variation of the LVDT, an inductive device. So here the primary coil is energized from an AC signal source oscillator circuit which then creates the induced voltages in the secondary coils. An additional circuit then demodulates the secondary voltages to a usable measurement signal with integral signal conditioning circuits intended for angular displacement and rotary positioning sensing. In all respects, it is identical in operation to use LVDT device, but the rotary motion imposes certain restrictions on its construction. So that is because of rotary construction, there are some restrictions in its usage. The span is given in angles and can be measured plus or minus 30 degrees to plus or minus 40 or even 60. Beyond that, output is non-linear. So up to 60 degrees plus or minus 60 degrees, it is best suited device. So this is the construction. It is same as LVDT only. You have one primary coil and two secondary coils, and core is a it is not a it is a circular one, whereas the core is a circular one. In LVDT, the core is a straighter one, whereas here it is a circular one. That is only difference between LVDT and RVDT. Response of an RVDT, this is the curve within up to 40 degrees, right? Up to 60, we can say it is linear type only, and when it goes beyond that, then it becomes non-linear, highly non-linear. So this is a simple type of RVDT. It is enclosed within a casing, and it is similar to LVDT only, but only the operation changes. Advantages of RVDT: low sensitivity to temperature, primary voltage and frequency variations, robust and compact construction, low cost, simple control electronics, longer life, high reliability and accuracy, repeatable performance. Repeatability is good. Custom electrical and mechanical designs. So typical applications are flight control, actuation, navigation, fuel control valves, cockpit controls, nose wheel steering systems, missile fin actuation. So these are the typical applications of RVDTs. And textbooks, you can refer same textbooks, and you can also refer A.K. Ghosh, Instrumentation and Control by A.K. Ghosh. That is really a very good book for all this type of sensors. We stop here. We will see another type of sensor in next session. Thank you students.